discussing the torque of a circular shaft, or solving the torque problem for a circular shaft twisted by a couple M. This is a circular shaft which torque is applied. Considering a circular cylinder of length radius, it is fixed at the one side it is fixed one end, and the couple mz is applied along the axis. Under the action of the couple, the beam get twisted and the generators originally parallel to z-axis are transformed into a helical curve. Since the cross-section is symmetrical, and so the cross-section of the cylinder is normal to the z-axis, remain to be plane after the deformation, and the couple only rotates every section through an angle theta proportional to its distance from the fixed end. Theta is equal to alpha z. Alpha is the twist per unit length, and the relative angle displacement of a pair of cross section or unit distance apart. This is a shaft where this is theta, this is beta initial, and after the displacement is x plus u, y plus u, u and b. This is angle beta. This is torque along txy, this is tau and tau zx, and this is v. If the cross section of the cylinder remains to be plane after the deformations, then the distance displacement along the z-axis is, let pxy be any point in a circular cross sections after the deformations. The point P occupies a new positions P x plus u y plus v. We choose that r of beta as a polar coordinates of the cross sections. We get u is equal to r cos of b theta plus r cos of beta. Now cos of a plus b is formula applying. R cos of beta cos of beta cos of theta minus r sine of beta sine of theta minus r cos of beta. Now taking cos of beta and cos of beta as a common, cos of beta minus 1 minus r sine of beta sine of theta. Now sine theta is small, and x is equal to, taking x is equal to r cos of beta, y is equal to r sine of beta. So we getting x is equal to u x minus cos of beta, y minus sine theta. Now again theta is small, so 1 minus 1 is equal to 0, which is equal to minus y theta, so u is equal to minus theta. Similarly, v is equal to r sine of theta b theta minus r sine of theta. Sine a plus b is cos of taking formula, so r sine of beta cos of theta plus r cos of beta sine of theta minus r sine of beta. So again in case of r sine of beta y, so cos of theta r x cos of beta is equal to x minus r sine of beta is y. So taking y common, cos of theta minus 1 x sine of theta. Again theta is small, so theta is 1 minus 1 is equal to 0, so x theta, so we have y is equal to minus theta, u is equal to minus theta y, and v is equal to theta x. And if theta of yz we can write as the displacement at any point of p from u is equal to alpha zy and v is equal to alpha zx, where w is 0. Applying the formula for the strain components, we get exx, eyy, ezz, eyz, or e is equal to minus alpha y. So exy is equal to 0, eyz is equal to plus 1 upon half alpha x. Applying the stress strain relation, we get tau zy is equal to mu alpha x, tau zx is equal to minus alpha y, tau xx, tau yy, tau zz, tau xy is 0. So this system of stress satisfying the equation of equilibrium with the no body force acting, and the equation of the compatibility is the boundary conditions for this problem are as follows. The surface integral r of tau zx dxy is equal to surface integral r of y dy dx is 0. Since r is a circle, so a square y square is equal to 0, y is equal to a square minus a is equal to 0, y is 0. So mz is the surface integral of tau x zy minus tau y zx. In case of tau zy and tau z, we substituting their values. So surface integral x mu alpha x plus y mu alpha y bracket close dx dy, which is equal to surface integral r x square mu alpha y square mu alpha dx dy. So which is equal to mu alpha surface integral bracket starts x square plus y square bracket close dx dy, separating x and y. So mu alpha surface integral x dx y mu alpha y square dx dy. So which is equal to mu alpha a cube upon 4a plus mu alpha a cube upon 4a. So which is further equal to 2 mu a alpha pi a 4 upon 4, which is 1 upon 2 mu alpha pi a 4. So mz is equal to mu a0, where I0 is the polar moment of inertia for the circular cross sections of the radius a. In case of hollow cylinder, I0 is equal to pi a raised to power 4 upon 2 bracket start 1 minus b raised to power 4 upon a raised to power 4, where a and b are the respectively the outer and the inner radii of the cylinder. There is no tractions of the movement acting any other part of the body. All the boundary conditions are identically satisfied. The stress vector at any point xy of the cross section z constant is given by tau vector is equal to I t vector is equal to I t zx plus j t zy k zz, which is equal to mu alpha bracket starts minus xy jx bracket close, which is equal to under root of tau zx square plus tau zy square, which is equal to mu alpha under root of x square plus y square, which is equal to mu alpha r. This is the maximum circumference of the cross section of the cylinder. There we have I upon r is equal to mz upon I0, which is equal to mu alpha. Therefore the factor by which we divide the torque to obtain is called